So how do we know that current in a wire is carried by electrons and not protons? This following experiment actually does more than demonstrate that electrons do the needful. It also allows you to measure the number density of charge carriers N. Now, if you recall earlier in defining Ohm's law is a combination of two statements, and that is J equals sigma con times the electric field, which gives you a relationship between the current density in a wire and the conductivity of the material of which the wire is made and the applied electric field. Now, there's also a more fundamental equation, and that is the current density in a wire is given by the number density of charges times the value of the charge carrier. It could be the electron's charge, so I'll write it as E, times a velocity known as the drift velocity. In one of the homework assignments, I had you estimate the drift velocity in a 20 ampere 10 gauge copper wire for extra credit. Now, that calculation, if any of you tried that, required you to get the number density N using some atomic hypotheses. Now, one of the slightly shaky things you would have done if you had done that calculation is to estimate the valency of copper. Now, the valency of copper is a very complicated thing. It varies between 1 and 2 depending on temperature and various other purity factors of the copper material. So it's a very shaky calculation indeed. This actually gives you an experimental estimate, a pretty good estimate of the number density of charge carriers for that given sample. So no assumptions need to be made and no theory required. So how does this work? First, you have a piece of metal. It could be anything, okay? And you connect it to a circuit, which means that you make one end at a higher potential than the other end. Let's say we put this end at a potential V and we ground the other end. So now current's going to flow, and well, there are two possibilities. One is the current is made up of positive charges, the other is it's made up of negative charges. Let's take the positive charge hypothesis first. If current's made up of positive charges, then positive charges will flow from the higher potential to the lower potential. In other words, you're going to have a positively charged particle, which I'll write as plus, drifting with drift velocity Vd in this direction. Now we can apply a magnetic field to this sample. Usually it's applied, the sample is not that big, it's actually a very small sample, about the size of your fingernail. And so you apply very strong magnet on either side of it. Let's assume that the magnet points into the page. The magnetic field, points into the page. Okay. So what's going to happen? Now we have to use the rules that we learned for magnetic fields. Magnetic force, Fb, acting on a charged particle of charge Q, is given by Fb equals Q times V cross B. In this case, the V is the drift velocity. Let's find out what V cross B is first. That's always a good thing to do as an intermediate procedure. So V is to the right, B is into the page, so follow your right hand rule. Keep your fingers to the right first, because that's the direction of V, and then curl it into the direction of B. The direction of B is down the page, so you're going to curl it like that. And then you'll find that V cross B is up. Now that's interesting. It means that if the charges are positive, then positive charges are going to accumulate up there, because the magnetic force will also be up if it's positive, Q is positive. So let's write this. If Q is bigger than 0, Fb is up. So plus on top. Well, this metal conductor in real time is neutral. So if plus end up on top, minus end up below. So I'll write that too. What happens if Q is less than 0 though? If Q is less than 0, then a couple things are going to happen. If the charge carriers are electrons, first of all, the drift velocity will be in the opposite direction because electrons travel from the ground to the higher potential. So first of all, I have to reverse the direction of V. If I reverse the direction of V, then what's going to happen is that V cross B, if this is V and that's B, V crosses B is going to be down. But Q times V cross B is still going to be up because Q is less than 0. So it's going to end up having negative signs on top because now the charge carriers are going to be negative. So I'll write this. If Q is less than 0, FB is down. So minus on top plus below. Well, FB is still up is what I should have written. It's still up. I mean, V cross B is down, but FB is still up. So this is an interesting characteristic of this experiment. It actually helps us determine what's going on, if it's electrons that are doing the talking or if it is protons. And how do you do this in real time? Well, after a while, I mean, the while is not long at all, it's a few milliseconds, you have to attach what's called a galvanometer to this galvanometer probe to the two sides. Okay, so this galvanometer is a big meter with a deflector. You can see this in some old-fashioned labs. It's got a mirror to make sure you're not having any parallax phenomena, and then it's got terminals, usually 2 or 3 or 4 down there. And then there's a needle which either points to the left or to the right. Let's say it points to the left if the positive charges accumulate on the top. That proves that the charge carriers are positive. And in some cases, they are sometimes positive. Not all metals, for example, some semiconductors have that feature. But for metals, we're talking about metals, the charge carrier always ends up being negative. So the needle will deflect, in this case, to the right, which means that it's proven for us once and for all that the charge carriers are negative. But be that as it may, Benjamin Franklin's convention is very powerful, and as I told you when we discussed Kirchhoff's law, the power of the convention is that we can use various analogies like climbing up and down mountains and thinking about hiking, loss of potential, gain in potential. So we continue to maintain the fiction that current is carried by positive charges. Why not? It's still useful. Although this experiment once and for all proved that it's not the case. So let's assume still, even this is like insulting Hall, but let's go ahead and do that. We're going to assume that current is going to be positive charges. So let's use the first line then. FB is up, so plus on top. So all the plus charges will end up on top. I'll write that here. And then minus charges will end up below. Well, what's that going to do? Eventually, when a steady state is reached, that will create an electric field. Let's draw the direction of that electric field using a vector. The electric field points from positive to negative, higher potential to lower potential, where the potential I'm referring to is this potential. This is sometimes called the Hall potential. So this is the Hall electric field, EH. Now what does the Hall electric field do? If it's a positive charge that's carrying the current, which we're going to assume it is, then the electric force, Fe, is going to be Q times E. Well, that simply means that the electric force is going to be in the direction of the Hall electric field. It's going to be down. Well, remember, for the positive charge, charge carrying current case, the FB was up. Now Fe is down. After a little while, there's going to be equilibrium. Fe is going to be equal to Fb in magnitude. Said another way, if the equilibrium is not yet achieved, if electric field is really small, then charges will continue to go up and sit there like little birds perched on a telegraph wire, and these are anti-birds, till the equilibrium is attained. And once the equilibrium is attained, these charges will stop migrating like that. Okay, so that's the equilibrium condition. Let's work it out and see what we get from the equilibrium condition. The electric field is Q times, electric force is Q times E. The magnetic force is QVB sine 90 degrees, because the angle between the velocity, drift velocity, and the magnetic field is 90 degrees. Of course, Q cancels out, so it doesn't even matter at the end what Hall thought. So this gives us an interesting relationship. It tells us what the drift velocity is. The drift velocity is actually given by a formula. It's the ratio of the electric field to the magnetic field in equilibrium. Now we can run back to that formula. Now the current in a wire can be found by simply measuring it using an ammeter, putting an ammeter here. So we'll assume that the current is known, okay, in this situation. If the current is known by putting an ammeter in series with the Hall probe, probably call it something, it's called the Hall probe, then we will know the current. So I is known, but I is related to J as follows. I over the area of perpendicular cross section is precisely J in magnitude. So this tells us that J is equal to the current, which is known, divided by the cross-sectional area. Remember, that is not this, it is W times T, because the current is flowing in this direction. So the cross-sectional area is whatever occurs perpendicular to it. So that W times T. Well, these are measurements that you can easily make using a not exactly meter stick, a finer device than that. So once you can, let's call this equation 1. We can put this back in equation 1, and I get I over Wt equals n times the magnitude of the charge of an electron, which everybody knows, times the drift velocity, which is E over B. Well, what does that tell us? It tells us the number density, n, is equal to I times B over n, sorry, not n again. It's E times WTE. The only thing we have to worry about is this E. What is E? Well, that is measured using another voltmeter attached between this part. So you throw out the galvanometer and substitute a voltmeter in its place, and that's called the Hall voltage. So you measure the Hall voltage VH using a voltmeter, and of course over the small distance the electric field is pretty constant, so we can use the fact that the electric field E is the Hall electric field EH. Been a little careless with my subscript here, is going to be equal to the voltage that you measure divided by the distance W. So let's put that back in that formula. So it's IB over E times WT VH over W. Well, turns out that even W is not important to measure, so the only thing you really need to know about this probe is the thickness. So this is I times B divided by E times T times the Hall voltage. A completely amazing formula is this formula. By measuring the current through an ammeter, by measuring the voltage using a voltmeter, by knowing the magnetic field, this magnetic field is external and it's controlled by you, by knowing that magnetic field and by measuring the thickness, you can find the number density of participating charge carriers in a complicated atomic situation. Truly remarkable fact.